Welcome to this session of Shadow the Scientist, Inside the CHARA Array and the Power of Interferometry. My name is Jamika Marshall, and I am the Programs Manager for Shadow the Scientist. The Shadow the Scientist initiative is brought to you by an incredible team of people at the University of California, Santa Cruz, and we are funded through a generous grant from the Heising Simons Foundation. Again, I'd like to welcome you to this very special session of Shadow the Scientist. This session is for you, students at the Los Angeles Pierce College, for your STEM week. We're thrilled to have you. And this session, we will be shadowing Dr. Nick Scott and Dr. Cyprian Latherman. So just a bit about the CHARA Array. Now, in this session, you are going to be stepping behind the scenes of the cutting edge astronomy happening at the CHARA Array, which is one of the most powerful optical interferometers in the world. If you aren't already familiar with CHARA, it's actually located on the historic Mount Wilson Observatory in California. Now, CHARA combines the light from 6 telescopes spread across the mountain using an incredible technique called interferometry. And this achieves a resolving power of a telescope that is hundreds of meters wide and allowing astronomers to study stellar surfaces, binary star systems, and other phenomena in extraordinary detail. Now, without further ado, let me get us started with Nick Scott. Welcome, Nick.
Hey, thanks, Jamika. That was a great intro. Yeah,
Thank
you
you.
guys are lucky in that this is literally in your backyard. If you've been to looked up from Pasadena toward the mountains and you see some kind of white specks on the top of the mountain, it's pretty easy to see the 150-foot solar tower and the 50-foot solar tower, as well as if you're lucky, the 100-inch dome from many parts of LA. So Mount Wilson is open to the public. It's a nonprofit. It's a historic observatory. You can come up and walk around. It's nice because it's a lot cooler up here than it is in the valley. So if you can make it up, it's really worthwhile. And then CHARA, the Center for High Angular Resolution Astronomy Array, is located on top of Mount Wilson, and we share the grounds with the historic observatory. And what's interesting is this was the birthplace of this technique at the 100-inch telescope, and now we're doing the cutting edge modern version. Um, Another way to put it, interferometry is a mouthful and often it's confusing to people. Another way to put it is we build optical telescope arrays. So somewhere, if you've ever seen the movie Contact or heard of like radio telescope arrays, those are also interferometers, just a different type. And it's hooking up many small telescopes, relatively small ones, to simulate the power of one giant telescope. So I'll share my screen and show you some little details about it. All right, let's see. So we have a relatively small staff. There's about 16 people total that work at CHARA. Some here, some in Atlanta. We're a product of the Georgia State University, even though we're here in California. About a dozen of these are scientists, and we all work together to keep the array running. When you say you're an astronomer, this is typically what people picture is old guy looking through an eyepiece on a giant tube. This is the 100-inch telescope that's up here on Mount Wilson. It is currently can be used by the public, can be rented, and you can come and tour it. But it's not used for science anymore. And astronomy is, kind of cutting edge on new detectors, new cameras, and we'll see some of those when Cyprian takes us his laptop through the lab. Another more modern example, this is where Jamaica is. This is Mauna Kea. This is the best telescopes in the world on top of Mauna Kea. And these are monolithic, giant telescopes where it's a single big mirror. They don't function together as an array. So our angular resolution is the term that'll come up a lot, is how small a details we can see. Stars are very, very big, but they're very, very, very far away. So they appear incredibly small in the sky. So in order to resolve them, to pick out the details, you need an extremely large telescope. And even though if you see this like dump truck for scale, this is the Gemini telescope is massive, it is still tiny compared to what we can do with these arrays of telescopes. I mean, this is inside of that. You see people for scale. This is an 8-meter telescope. For comparison, at the CHARA Array, our smallest baseline, so it's what we measure the distance between our telescopes, is 34 meters. So already much bigger than this. And then we go up to 330 meters. So this is the historic telescope, the historic 100-inch, and the 20-foot interferometers. This is an old science, but it's been benefiting from modern technology, like some of the detectors and cameras we use now. Um, Interference is just that we may take advantage of the fact that light's a wave, and that coming from the stars, it's traveling all together, and the light can interfere with itself, and we can, based on where we sample it, it tells us about the diameter of the star, or we can make images of the stars that are producing that light. So these are all these major large telescopes, some that have been made and some that hopefully will be made in the future, like the 30-meter telescope. And all of these are tiny compared to the resolution we get with the array. The trade-off is we don't get the sensitivity because it's like we're taking a cookie cutter across the mountain and we're just sampling a little bit of the light. We're not getting all that massive amount of light that these big telescopes get, but we do get the same resolution. So this is a lot of text, but I'm just going to say you may hear us talk about like degree, measures of angle is a degree, right? 360 degrees in a circle. If you subdivide a degree, we break it down into arc minutes and arc seconds. And you can go even further. So like the diameter of the full moon or the sun on the sky is about 30 arc minutes or about half a degree. We can break that down into arc seconds. It's 1800 arc seconds or milli arc seconds. Like millimeter is breaking up a meter. That's the full moon is 1.8 million milli arc seconds. And so why do we care about a milli arc second? That's about the size of some of the stars we're looking at. And that's about the same as looking at a coin from across the entire continental US. So that's the kind of resolutions we're looking at. Um, this is what the array looks like from above. So this is what you're seeing down in Pasadena or other parts of LA. This is the 50-foot solar tower, the 150-foot solar tower, the 100-inch telescope that I showed you inside, and the 60-inch telescope. And the CHARA telescopes are mixed in here. So this is one of ours. This is our shortest baseline here. This is 34 meters between them. But then back here we have another telescope and another here and another back here and back here. So all the way across the mountaintop in this big triangle, we have telescopes that work together. This is another view of it, and these are them circled. So, and the blue cross is where I'm sitting right now. This is our office, and we have this big lab in this long building here. So these are some of the largest telescopes in the world, just to show you kind of by scale compared to like a basketball court. This is Gemini North. It's that one I showed you the inside of. It's an 8-meter. Um, these extremely large telescopes are being built now, and so we will have telescopes that are on the 30 and 40-meter scale. But if I zoom out and show you that compared to the array, this is an aerial shot looking down on the mountain. This is how big our telescope array is. And then this is that long building that Cyprian will take us into later. And so it's as if you have one big mirror that's this size of the whole mountaintop. And the way we do that is we need to feed the light from all these telescopes into these pipes and into the lab where we can combine the light. So we have to physically bring the light from each telescope all together and mix it in the lab in order to produce these measurements and these images. So this gives you an idea of if you drew lines between every telescope, these are all the little connection points. Let me skip ahead. So this is us. So this is where we're at. This is that long lab. And then these are the parts of the CHARA array here. So we go from 34 meter to 331 meter. And then inside we have all these different ways to control the light. So first thing we have is a telescope, and Cyprian will take us out to one of those. Light comes in the top, bounces off the primary mirror here to the secondary, to a third mirror, off to the side. It goes through an adaptive optic system that helps clean up the light for being distorted by the atmosphere. And then it goes down to the bottom of the telescope and into one of these pipes. And these pipes are vacuum pipes where all the air has been evacuated so that we don't have any turbulence that is going to distort the light at the ground level. And this goes all the way into the lab. So this is just kind of a schematic showing it goes around, down, and into the pipe. And we have an adaptive optic system like this on the side. So it's just a flexible mirror that and a very high-speed camera that measures the light and then cancels out any distortions from the atmosphere to just kind of clean up everything before it goes in the lab. And that helps our efficiency. And then inside the lab, we have these long rails and carts travel along these rails that have mirrors on them, and they work kind of like an optical trombone because for this technique to work, the light has to travel the exact same distance down to a fraction of the wavelength of light itself uh, through all of these different paths. And then it does all of this path it travels through before it finally gets to a camera at the very end. So light comes through these pipes, comes up a periscope, goes all the way down to the end to where these carts are moving. These carts during the night are traveling up and down these rails, and the light then gets reflected back behind this. This is another shot. These are what the carts look like here. So they're on little motors, and they run along this 45-meter path to these tables. Um, the light gets shrunk down to about an inch wide and then pass to these different mirrors here and into this other room where all the detectors and cameras and beam combiners are. And we also have another adaptive optic system within the lab here to even further clean up the light. And what this allows us to do at this point is we can pick any telescope to go to any different position inside to different cameras, to different instruments that have different purposes inside the lab. And that's what these tables are. Pretty much each table here is a different instrument. And it's kind of an overview of all the different things. The way to I usually explain to people is this is like a extremely expensive, complicated Lego set. You can keep building upon these things and you can put mirrors in. They're all in different stages that can move, but all of it is just ways to transport the light very precisely to one of these cameras. And what's an instrument look like? It looks something like this. Uh, it gets less complicated once you like study these and play with them, but light comes in. This is just taking two beams, so two telescopes instead of all six. We have other instruments that take all six in, bounces it around, has mirrors that are motorized so we can control the tip and the tilt of the light, and then injects it into fibers. In this case, it goes into the fibers and then goes into a camera, and then we make our measurement. And all of this is controlled from a control room that's just in this office here, where you have a whole lot of different GUIs and interfaces that are tracking where the stars are for all six telescopes, what those carts are doing, and they're moving during the night, and making sure everything's running okay, checking the sky conditions. And all this is run by typically one operator and one scientist. And I think with that, Cyprian, if you want to head out to S2, we'll catch up with you there and take a look at the telescope.
Yep.
And then if anyone has any questions, I'm happy to, we can be interactive. I'll show you like what some of the science actually looks like that we do. Um, and why we care. One of the things we really care about in astronomy is the diameter of stars because that gives you a solid metric to then compare your models of how stellar interiors work. So stellar fusion, the different colors of stars, the type of stars, what their evolution is. And so this is what's called an HR diagram. And all of these circles are stars that have their diameters that have been measured here. So almost 700 stars that have very precise diameters measured using this technique. And so this works to constrain all of the theory. Astronomy kind of works in two branches. There's the observationalists, the people that work on taking the data, working the telescopes, all the different observing strategies, and then theorists that do modeling and on the physics side and go through and try and predict what we're going to see. One of the things most people don't know is about half the stars, when you look at the sky at night, are binary stars. That means there's two stars going around each other. And about a quarter of the stars you can see are triples or more. So it's kind of unusual that our sun is a single star. And this is important because binaries, by measuring their orbits, let us measure the masses of stars. If you know precisely the orbit of two things going around each other in space, you can determine their masses. And so that's something that's useful for, again, constraining the physics. Also, you can have these systems where, like, it's not just two stars going around each other or three. Castor is a system of six stars. So you've got a binary going around another binary with another binary, all orbiting each other. We can also do something that nowhere else except another interferometer in the southern hemisphere can do, run by the European agencies, uh, is measure the surfaces of stars, to actually produce images of stellar surfaces. And unlike our sun, which has spots on it, some of these stars have incredibly large spots, like you see here. And we can also measure their rotation and make images of the full surface of a star over the course of many days. So Cyprian's out of the telescope now. He's unlocking the cylinder door and going to go up. There's a ladder and then a raised surface, and then they will show us the telescope itself. Also with these called rapid rotators, since stars aren't solid, they're big balls of plasma. If they're rotating very rapidly, they'll bulge at the equator. So you notice a lot of these stars aren't actually round. And because they're bulging at the equator, the material is further away from the hot core, it's cooler. So you get what's called gravity darkening. You get this dark band around the center of the star because it's just so far away from its hot core.
Nick, we actually
Yep.
have a question that
Sure.
it's a perfect segue into what you were just talking about. And this is from the Shadow the Scientist founder who's with us, Raja Guhathakurta.
Okay.
Can the CHARA Array detect departures from sphericity for a star like Betelgeuse?
Yeah, actually can. Betelgeuse is tough because it's actually so big, we're over resolving it, meaning that we're seeing granulation of the star surface itself. But for other stars like these ones here, like Regulus, Hasselhag, Altair, these are images of these stars that we've made with the CHARA array. So you see this departure from sphericity. Um, we measure that. It's one of the first bits of science that the CHARA array did was measuring diameters. If you measure diameter over many axes, you get an image of the of the outline of the surface. But now with six telescopes, we can actually produce these images. So we can see not just the shape of it, we can see the details of these spots and hot spots and cool areas. So Cyprian is opening up the adaptive optics board now. So it's a 16-foot diameter dome and a 1 meter telescope inside it. And the telescope's built for rigidity. So I'm going to stop my share so we can make his bigger, I think. Is there a way to pin him and pull up his
Hmm.
Yep.
Absolutely.
And Cyprian, you're muted if you want to say anything, but hopefully you're hearing us.
Yeah, yeah, I am. I am. Just need to find the right way to open them.
Yeah.
Yeah. Yeah. So I have to
Yeah.
see.
So that's the adaptive optics board. So there's a camera right there in the middle. That's the wavefront sensor that detects the quality of how much the light's distorted by the atmosphere. There's this round kind of carousel are different filters that we can put in depending on what science we're doing. And then at the top, there's a mirror that's the deformable mirror that you can't really see because it's in shadow. It's a thin mirror with little push rods on the back of it and little solenoid, little actuators that push and pull to change the shape of the mirror. And so it moves it to the exact opposite of the shape of the wave of light and cancels that out. So you get nice, as if there's no atmosphere at all.
So yeah.
Yep. So it's a good view of the adapter. And we have lots of stuff on there that lasers, we can back inject beacons so we can send it back to the lab and we can measure. Because you imagine we've got a lot of reflections. And so that's the primary mirror under that accordion there. Yep. So
So
that's the
this
primary. You
cover
see how
is
big it
the
is. Yep.
cover.
Tertiary
Uh,
mirror. And you notice it's not made for a person to be in there all the time. Like there's cameras on the finder scope. During the night, it's just one operator in the control room and the telescopes are all working robotically.
So, Nick, Cyprian, during the day, do you all or other of your colleagues go out and do maintenance and setup on the telescopes here in preparation for your evening observing?
Yep. So Carolina is also one of our staff. She gets the lab all set up. Cyprian will get an instrument aligned. I'll work on the telescopes. We first thing in the morning is I get a email of tech report, what's broken during the night and what needs to be fixed. And we spend all day fixing the things to make sure we'll be good on sky the following night. Okay. I think Cyprian's good. You can head into the lab and we'll rejoin you there.
Yeah, we'll just close
Yep.
things.
And I'll answer some of the questions while you do. I see there's one of the most unexpected things the CHARA Array has revealed about the life and deaths of stars. Um, I think one of my favorites is it's not CHARA wasn't the first to do, but it confirmed it really nicely, is in astronomy, a lot of it has been done because until the array and until interferometry, you couldn't really see stars as anything other than a point source, right? Betelgeuse was the first one where we measured the diameter, and that was done with that Michelson interferometer, the 20-foot interferometer in 1920. But until more recent times, there really wasn't imaging of the stars themselves. And one of them is that astronomers for photometry, for measuring the brightness of stars, for measuring the spectra of stars, rely on what's called a standard star. And so we pick certain stars that we think are boring and that say, okay, this is our point we're measuring from. Like Vega is a very famous, very bright star. It sets what color is in astronomy. We say that Vega is 0 in every magnitude. It is the same brightness and every color, and then we measure relative to it. And we hope that that standard star is boring. It doesn't have a lot of spots. It's not aspherical. It should be a sphere. It should be not in any weird orientation. And all this stuff should be kind of a good standard. You want your ruler to be boring. You don't want a ruler that has a weird shape. Uh, what the CHARA Array, one of its early papers did was look at, well, Vega, this famous standard star, is a rapid rotator, meaning it's one of those that's spinning really fast. And so it's bulging at the equator. And we're not looking at it edge on, we're looking at it pole on. So we're seeing this temperature profile where instead of being cooler in the middle, it's hot in the middle, looking at where we're looking at. So like its North Pole is closer because it's spreading out. So its temperature profile, if you did a slice across it, is completely atypical. So it's a pole on rapid rotator standard star, which means it's about the worst standard you could have because it's really atypical in a really unusual orientation. Um, Jamika, I see your question about why do we care about high angular resolution? Why do we care about this when observing stars? The main reason that the array was built, or one of the main science drivers, was it's a binary star machine. Like I said, most stars are binary, and is if you take an intro astronomy class, that one of the first things you learn is how important mass is for a star. The initial mass of a star, when it forms, when it starts fusing hydrogen in its core, pretty much determines the entire life of that star. It's as if as a human, when you're born and they weigh you, that determines when you're going to die, what type of life you'll live, everything, all from that initial condition. Nothing in our world does that except stars. Like it's not in our experience to be like, oh, I know what this, my puppy weighed this much. I know he's going to live this long. Doesn't work that way. But with stars, that mass they have determines how much fuel they have, how fast they burn that fuel, how hot they burn, how their life cycle will end, whether they become a neutron star, whether they become a white dwarf, whether they become a black hole, all traces back to that initial mass. So it's really important to know the mass of stars. That constrains all of our equations that let us model the interiors of stars where fusion is going on. So, like trying to develop fusion power here on Earth, we need to understand what the conditions of the center of stars. All that can be done if you know the mass and a few other details. So to get the mass, like I said, a binary, it gives you a way to weigh the star. By how the two stars going around each other pull on each other, the orbit they form tells you the mass. So if you want to measure the orbit, you need to have a really good resolution telescope. And some of these orbits are very, very tight, meaning they're very close together. And the only way to measure the binaries is to have something like an interferometer. So what the CHARA array and other interferometers can do is give you the orbits of these stars incredibly precisely. And when you combine it with radial velocities, which is another technique, so we can see what the orbit is on this projection of the sky. Radial velocities, measuring the color shift as a star goes backwards and forwards in and out of the plane of the sky, meaning blue shift and red shift, gives you the third dimension component. So we can actually, when pairing our data with other telescopes that do radial velocities, get a 3D orbit of exactly how these stars are going around each other and doing it for, like I said, the multiple systems. So you see, Cyprian is now in the lab. It's a building within a building. So all that insulation and big kind of warehouse look. The actual careful part of the lab is that other box that he's right behind him right now. So it's a building within a building. Yep. And there's a little warning light above the exit sign. We've got a metrology laser in there. He's going to put on some booties on his shoes to make sure we don't track in any dust. And there's a little sticky pad he'll walk on to take the dust off the booties. Also in that area right there is all of our computing power. So we've got a rack of servers. You can imagine we've got a lot of computer systems to run everything. Yep.
Yeah, we have a lot.
Yeah. And then first part of the lab he'll be in is where all the beam combiners are.
This is a chariot one.
Yep.
So, yeah, it is all covered, but you can see.
You can show off Simmeril.
Yes, Silmaril, which is the one that I'm working on currently. So Melkix here with Mystic in the back, which is our backbone now, making most of the science that we do with them.
And most of those images that we've seen are coming from MERCX.
Yeah. So yeah, in the back more instruments. With speakers, the physical one.
It's a very full lab. And so, the light, if you could see the path of light, or we, had a laser going through, you could see that it just goes all the way across there, and we can have a light from any telescope to any one of those tables.
Yes.
So back so in this whole space, and I remember being there, I was so excited to be there and get this tour in person, Nick and Cyprian. And so just to give a sense of location, Cyprian was outside at first at one of the telescopes. Now he's come inside. What's the distance between the telescope that you showed us outside and then this facility? Because the light needs to travel all the way from here, from the telescope to there, right? So what's that distance and what kind of issues do you encounter in trying to make sure you capture all of that light?
Yeah, I would say it's about 100 meters, 150 meters typically to go between the center of the lab to any telescope. The widest we have separation between two telescopes is the 330 meters, but you only need half that to go to the middle. So it's basically, he's walking a football field. So we all, like when I come and check the telescopes during the day, it's not uncommon for me to get, 5-6 miles of walking in, going back and forth between telescopes.
Okay.
And see these long rails.
Yeah. Yes. So what happens with those long rails that we're seeing?
So the reason we need these carts, the whole time we're observing, these carts are moving the whole time, slowly, but they're chugging along on the special little tracks because the telescopes are all pointing at a star. And since the star is not exactly straight above, maybe it's off to one side, the light from that star is going to hit one telescope. And then very quickly afterwards, it'll hit the next telescope. But we need to do something with that time because we need the light to hit the detector, the camera, at the exact same time. So what we do is we take the light to hit the first telescope and we give it more distance to travel. So that's why it's like an optical trombone. These carts move and they track because the Earth's always rotating. That distance is always changing. And so we need to delay the light. So this is called optical path delay. We literally just give the light more distance to travel. And so we have a lot of math built into the software that calculates, and a laser that goes in the top little there that tells you exactly where the cart is, and then how far, what position it should be at, what speed it should travel, and it's just constantly moving back and forth all night. And it has to be accurate. We're going from 331 meters. It needs to move that cart accurately to less than a millionth of a meter.
So that kind of precision it's mind-boggling.
Yeah. Pull out one of your hairs.
Yeah,
and cut your hair about 100 times. It should be about that size in the diameter of the hair, not the length. So
that is absolutely incredible. And so is a part of is maintaining some of these facilities that we're seeing behind Cyprian. Is that part of your responsibilities, Nick, or Cyprian, or does kind of everyone kind of work as an engineer at CHARA?
we kind of all do everything we can. We have a Venn diagram for everything, you know. Sometimes I'm doing mechanical stuff, sometimes I'm doing optical, sometimes electronics. Same with Cyprian as instrument scientist. He does a lot of the work supporting visiting scientists because we're open to anyone that proposes to use the array, can write a proposal and it goes through a review process and you can be awarded time to use the array to do your science. And Cyprian is great at introducing the new scientists to the array, what they need to do to get good data, how to reduce that data, as well as working on the Simmerl instrument.
Yeah. So Cyprian, you were just showing us there was a table there behind you with lots of different mirrors at different angles. And right now we have, I think you have something else behind us too that's very similar. Can you explain what we're seeing here on this particular bench?
Yeah, so basically we have the beam samplers that are on the back. So each uh, beam will have a different position to send it to an instrument. We can change the beam order depending on the instrument and everything. And so it will send the light either on the visible path, which is on the right for me. I'm not sure which
Yep.
side for you. And the IR, so the infrared on the left. And so we have a multiplicity of things. So for instance, the mirror here, actually to get what we call a six telescope simulator, so STS, which allow us to simulate having the three telescope, but in the with lab light. So way more stable, and we can do that whatever the time, the weather, and things like that. So it's very great to actually uh, make sure that everything on the instrument are good. But we also have one which is just don't want to make
Nope.
the
The
laptop
laptop.
fall. So those ones here actually take some of the light that comes from the telescopes, and also we can do that through the STS and send it to what we call six telescope star tracker, which will allow us to see if the light coming from the star is has a weird shape or is round, which indicates some AO performance, so correcting the atmosphere properly, or just if the telescopes are aligned because they have a reference position, and so if the light doesn't fall on this position, it means that there is some misalignment, and it means that the instrument after that won't see the light. So yeah. So that's
Yes.
a kind of thing that we have here, and we can do that both in visible and in the infrared. And so yeah.
And we have so light's going all the way from the telescope through 20 something reflections, all to be injected into a single optical fiber in some cases.
Yeah.
And so there's lots of moving mirrors that's all got to work perfectly and be aligned.
Yeah, and that's just the telescope side. Those are the instrument side that have kind of the same. So here we have one that's separate between two different wavelengths. So the K band for Mystic and the H band for me for Merkix, which allow us to have different information at the same time because we are observing both at the same time. Then the light is picked up from Merkix and sent on those mirrors that is then sent in polarization plate, because polarization is actually very important for the fringes. If you don't have, if you have a mismatch in the polarization, your fringes will have a very low contrast. And so we need to correct for that, especially because we are using fiber optics in most of our instruments now.
Yeah.
So as you can see, the light comes, hits this mirror, and we'll need to focus this mirror on the tip of the fiber optic to get as much light as we can in this fiber optics, which then are sent in the camera with different purposes.
Yeah.
So yeah.
And we can operate not just two colors at once. We can, and we're working on improving doing three colors at once. So three different instruments, all taking light from six telescopes simultaneously.
Yeah.
So and that lets us get really good images and good data.
Yeah, and working to get a fourth one that would work at the same time.
Yeah.
So, so
And
yeah,
a
so
lot of that's due to the fact that we have collaboration with many different universities and different partners. So
Yeah.
that's, GSU built the array, and then the Keck Foundation funded a sixth telescope, and GSU only built one beam combiner. All this other stuff in the lab is because of the CHARA consortium. We have Sydney University, Paris Observatory, Michigan University, um, Côte d'Azur, Nice, Exeter, Kyoto Sango in Japan.
Yeah.
So do all of those partners get a certain amount of time on Chara?
Uh, the consortium has its own like block of time where they can apply for. So they still go through a review process to get allocated time, and then we have 100 nights a year that are open to anyone through NORLab. So anyone can apply through NORLab, which is the astronomy organization for the USA, and can get this time. And one of CIPIAN's jobs is to support astronomers that may have never done interferometry before and getting that data. So this is really, it's a public service for the community.
And helping them actually have time as well, because going through the process of the proposal with interferometry, it's a bit different from other techniques. So they need some insight on how to properly justify the time they need and choose their instruments wisely and stuff like that. So
And we try to demystify the science. So even in
yeah,
astronomy, interferometry has always been kind of a scary black box, but it's become more and more accepted and used, throughout the field. And there's a little bit of a barrier to entry, and we want to, part of this program is to lower that barrier. So you don't have to be an interferometrist. We'll help you with the interferometry part. You just got to be a good scientist.
Ah,
yeah,
that's brilliant. That's brilliant. And so when I think about, and we have some questions from our participants here in the chat, I'm going to get to in just a moment. But when I think about, of course, this is the STEM, part of the STEM week here at LA Pierce College. What kinds of internships or opportunities might students be able to apply for in working in the lab, working with your instrumentations or electronics, for example?
Yeah. We have a couple ways. It's a challenge right now because funding is always tight, and we want to always fund our interns. We don't want to make you work for free. We have one student right now working with me, Noy Hakobian, who came to me through a community college. So he's studying to be an electrical engineer. He's now at UC Irvine, and so we have, we're most of us are scientists. We're not engineers, so we're doing engineering work, but we're scientists. But the array, it's kind of all hands on deck, keep it running, do whatever we can. So always happy to have, other STEM people to help that can, we can pass projects to. So we try to have at least one or two interns a year. But that's something that both I used to also work and I can still collaborate with NASA. NASA has internships, do apply. It's amazing how many internships like very few people apply to. So if you, have some skill and want to try it, apply for it. It's really good work.
Where could they find out information about opportunities with Chara?
Currently we don't have, I think on our website we have our contact info, or just usually people directly email me, but or I'll put out a call when I have something. But I can put my, feel free to share my email. I can put it in there, and I keep a list. Here, I'll put mine in the chat.
Okay, perfect. Thank you. Thank you
Yeah.
so much.
yeah.
So,
And
yes,
yeah,
Cyprian.
just wanted to add, if you are in a program that do astrophysics and you want to use CHARA, don't hesitate to contact us and try to get observation with us.
Yeah.
As we said, with Noir Lab, happy to help. If you think about doing a PhD, try to see the GSU program,
Yeah.
as they are highly linked with us. We are employed by them, and so their student is actually working a lot with us when they need data and stuff. So we have ways to have access to us. Just I think each person will have a different things to do, so don't hesitate to contact us, and we'll see what we can do.
Yeah. Yeah, like I said, Georgia State is, I came to Chara because of Georgia State. All right, sorry, I came to Georgia State because of Chara. I heard about Chara. I was like, that sounds really cool. What's this Georgia State place? And now I work here. So, it's if you're interested in stellar astrophysics, it's a great school for it. There's a lot of expertise.
Wonderful. Thank you so much, Cyprian. Thank you, Nick.
Yeah.
Okay, so we have a question from Anne Marie. What is the most deformed star that has ever been spotted with the CHARA array?
I don't know if I've ever thought of it as a terms of a deformed star, but as far as those spread out, probably those images I showed you. I don't know if one's like the most of any other. There is a limit because if the star spins too fast, it's not going to be able to hold the material and it will lose material. But I think some of those are the really rapid rotators, are the least spherical stars.
So would a rapid rotator include like a magnetar or
Yeah,
something?
if I think most of the magnetars are too small for us to resolve, but that would be another example on if it was a neutron star. These are all evolved stars. These are puffed up red giant stars, typically.
Yeah. There is
I
also contact binaries
Oh yeah.
that's a
Yeah.
presentation I gave a few months ago. And so you see this is two stars rotating around each other, and you see deformation because there is actually mass transfer between one to the other. And so I
Yeah.
guess we can call that very
Yeah.
deformed.
Yeah. The star looks like a peanut. That's pretty deformed.
Yeah.
Yeah, it's
perfect,
just it's
Cyprian.
really cool to get to see stars as full three-dimensional objects. Really in astronomy, you typically think of them as point sources of light.
So true, so true. I have a follow-up question, which is some of you in the chat may know of SOHO. And SOHO looks, of course, at the sun, and it's giving us incredibly detailed views of the surface of the sun. Now, compared to CHARA, the resolution and detail that we're able to see with in those SOHO images, how does that compare to CHARA images?
Well, nothing beats being closer to your object, right? If you look at uh, Voyager images of even the Voyager was 1970s, there's still some of the best images we have of like Neptune because it literally flew right up to it. And same with Soho, it's looking at the sun, it's very close to the sun relatively. So we can't get quite that good. But the best we can do is, like I said, with like Betelgeuse or something very large, we can try and actually get good images of that, even though the challenge is that it's just so over resolved. Um, but typically, some of the ones like I showed, let me see if I can share again. Images like this are kind of about as good as we can get currently. Now we're working on extending our baselines to go up to like a kilometer one day in the future with funding, we hope. And then we could get really insane resolutions. And we're also wanting to get more sensitivity. I'd love to have larger telescopes.
Well, we'll be looking forward to that, Nick. Okay, next question from Keslin. Is there any degradation in the quality of light after so many reflections and traveling so far?
So that's the trade-off, right? Even if you have a perfect mirror, aluminum mirror, perfect coating, brand new, you're getting maybe 98% of the light off it. And you have a second mirror, it's 0.98 times 0.98. And so it's 0.98 raised to the number of mirrors. So if you take 0.98 raised to the power of 20 something before it's getting to a detector, you end up with a very small percentage. And then if it's going into fibers, you lose a little bit of light, but you gain some stability. Um, in the end, we're getting about a couple percent of the light that we observe to the camera. And that's our trade-off. That's why we want bigger telescopes because you get we get high resolution, but we have unfortunately low sensitivity. And so like the instrument Cyprian's working on is to try and be as sensitive as possible, as few reflections as possible. And there's some neat tricks. I don't know if you want to talk about Cyprian of like what a Narcissus mirror is and some of the weird tricks you can put in there to try and make it as sensitive as possible. But a lot of it comes down to how good those detectors are.
Mhm. Yes, Cyprian, would you care to add to that?
Yeah, I mean, it's basically what I'm trying to do with Silmaril is to improve the throughput the total throughput by adding as few reflection and as few optical elements as possible, which is also a trade-off because it means that we have way less stability. So the beams will start to drift or to shake, and we lose some sensitivity, so some fringe contrast. So we need to find some tricks and stuff to make it work. But yeah, that's basically our life as interferometrists. We are trying to get things better by changing a bit something, but it means that we need to do
Yeah.
something else on the side to try to correct for the things that it was corrected as well. So yeah, it's pretty challenging for the brain, which is pretty good in my opinion.
Mhm.
So yeah, what Nick was telling is that as we are observing in the near infrared, we have a lot of thermal background because you know that everything emits light in the near infrared because we are at the temperature where it emits. And so what we want is to reduce the thermal background that come from all around. And to do that, usually we just put the instrument. Let me see if I go there. We put the optical element of the instrument in a big cold box, which we call a cold dewar. So that's the case for Mystic. But the thing is that it will reduce your throughput because there is optical element that you need to go through to go in the box. And so what we try to do with Silmaril is to put just here what we call a Narcissus mirror. And it's called like that because it means that the camera will only see itself, its own reflection. And the camera is already cooled at 80 Kelvin, so it has very low thermal background. And so it will just see the reflection of its own thermal background. And in the mirror, there is a hole that will just let through the science beams. And that's how we hope to reduce the thermal background without actually adding any optical element that the science beam will go through.
Yeah.
So yeah.
Yeah. So anywhere that camera, from the camera's point of view, when it's looking, if you were like your face was where the detector is looking out, the only place you'll see anything other than yourself is where the science light's coming in
Yeah.
instead of seeing the rest of the lab.
So, Cyprian, last time, and Nick, last time when I was there with you all, I was really shocked at how important HVAC work and expertise is at CHARA. Could you talk to us a little bit about that? Because there are so many pathways to contributing to the success of an observatory. And so specifically for CHARA, you were talking to me about how necessary those skills are.
Yeah.
Maybe Nick, could you
Yeah.
start us off?
Yeah. Like I said, we have 16 members of staff, and some of those, a few of those are back in Atlanta. So on the mountain, we have, just about a dozen people max, usually less than that. And our org chart's flat. We have scientists, we have technicians, we have site managers, and it's all just equal. We all have to contribute to make everything work. Um, it's anything from doing our own electrical work. You can imagine to keep the lab stable, there's a very complicated system for the air conditioning units and the air handling. There's electrical stuff, there's network engineering stuff, there's the computing. It's all sorts of systems that all have to work together. At any given day, we may be, digging a trench or fixing a broken pipeline or looking for a water leak or doing some incredibly complicated stuff in the lab. That's the actual science part.
And Cyprian, do you have anything you'd like to add to that?
Uh, to add, I don't know, but yeah, as Nick said, so there is multiple way to actually help doing astrophysics and astronomy because we need the scientists that need the data to actually do the science and stuff. So without them, we have no purpose. But in the meantime, the people that build the instruments, that build the telescope, that maintain them, that make sure that the electricity is always on when we need it, and stuff like that. The operators that just move the telescope, but it's six telescope for for the whole thing with different optical element and stuff. So there is different level and different knowledge and expertise that we need. And so yeah, you can reach astrophysics through a multitude of way.
Yeah.
Whichever you think is the best for you. That's
And it's one of the things that people don't often think about with astronomy is we're often in remote, harsh environments. We have a snowplow up here that we have to use. We're in LA, but we have snow. You just don't know. And that's one of the challenges of astronomy is that we have to deal with the environment, we have to deal with weather, uh, preparation for fires, all sorts of stuff.
So when we talk about the data that you collect, and you have, let's say, an astronomer there, they've joined you on site at CHARA for to get their data. Would they be in the room where we see Cyprian? And what does raw data look like from CHARA?
Um, we always encourage if someone hasn't worked with Charta before to come here in person at least once because it gives you an appreciation for everything that goes into keeping the array running, what the operator is doing. So just you have kind of the context for it. And then once the scientists are more familiar, a lot of them will join remotely. And it may just be the operator running the telescopes and someone on Discord that's doing collecting their data. Um, the data itself is what's called a FITS file. It's an image transfer format. It depends on for different instruments, but it's typically an image or table with what's called a header. So it has all the header information of when it was observed, what was observed, how it was observed, what settings of different things. And all this gets saved, archived. We have an archive in Atlanta where everything gets sent back to there to be backed up, and then the data gets reduced where you do calibrations of the data and there's a lot of software that goes into getting something that's usable for a science paper. But we generate, oh, and how many terabytes a year do we generate?
Of the raw data, maybe.
Yeah. All right. So yeah, about 100 terabytes a year. And then it gets reduced down, but that's why it's data reduction. It means you save the calibrate it and save the useful stuff, and your raw data you don't really have to keep. You can if you want, but you don't have to. But the raw data gets really big really quick.
Yeah, especially when you add spectral resolution, which means that you have more pixels on your cameras that are recorded, and so it just mean bigger pictures. And so
Yep.
that adds up pretty quickly.
I think we may have lost Jamaica. I wonder if the storm got worse in Hilo.
Yeah. So don't hesitate if you have questions while
Yeah.
Jamaica is not in line. Things that you want us to discuss about.
One of the things I'll add is that it's one of the things I like in astronomy. It's a very international field. We have lots of collaborators from different countries. People come here to work. They bring instruments. We travel to go to different telescopes or to go to conferences. So there's a significant amount of travel involved in being an astronomer, which is nice. Any other questions? You can go through. Let's see. Cyprian, you want to show the control room, maybe?
Yeah, I can.
Yeah.
Just
And
need
I
to-
can. Let's see. Uh, I'll share my screen and show something else while we're doing that. One of the other interesting things we can look at is a lot of stars, when they're forming, these young stars have disks around them, and we can image these disks. So not just the stars at the center, but it has this disk going around it, and we can notice spots and features in these disks that are co-rotating. And what this may be is signs of planetary formation happening further out and causing a vortex or piling up of material, wake, basically, in this hot material closer into the star. So a lot of science is, of course, looking at exoplanets. This is an interesting one. This is a binary pair. So a pair of stars going around each other, but then the disk is oriented 90 degrees, like face up. So they're going around each other this way, and the disk is this way. And this may be a planet formed within here, creating the central cavity. And if so, that makes it the first example of a polar circumbinary planet. So a planet going around a pair of stars and going not in the same orientation as the stars are going around each other. I'll stop sharing, and Cyprian's in the control room. So this is where the operator spends their night.
So what you have is kind of a small room with a lot of screens. And so you can see that, so those ones are the ones used by the operators, with some of the GUIs still open because we keep them open. And so you can see that each telescope have its own control and stuff. And this side is actually when we perform engineering on AO, which happens often because the AO needs a lot of care. And so, yeah, so we have this, and just next to it, we have what I think we could call the observing room. So usually we operate the instrument when we are observing from the mountain, from either this one for Merkix and Mystic and Smile, or this one, which is turn off now for speaker. And so, yeah.
Okay. Welcome back, Jamaica. Hopefully the storm's not getting too bad.
Thank you. Yeah, we've had some really bad lightning strikes that just happened and everything went out for a few moments, but I'm back, so I apologize. Okay, so we're in the control room, right? That's where we were just a minute ago with Cyprian. Okay, have we talked about fringes yet? Because I'm so excited about fringes.
So yeah, so fringes, if this is STEM week, hopefully if you've done any physics, you've heard of Young's two-slit experiment. It's very famous where there's if you have light and it goes through two slits, so it's just two little tiny holes, on the back wall from that, you'll see an image of what's called fringes, of bands of light and dark. And this is one of the historical experiments that first showed that light is not just a particle, but also travels as a wave and can interfere. Another way to look at it is like when you have two waves, like if you drop two rocks in a pond and the waves come toward each other, they'll sometimes ride up on top of each other. It's called constructive interference. They get bigger, and sometimes they'll cancel out and you get no interference, no wave at all. Or you may see this at the beach when you see two waves kind of swells coming toward each other. Sometimes they'll pile up and they'll get really high. Sometimes they'll cancel out. So light does the same thing. And all of this stuff I've shown you, the measure of diameters, the images of the spots in the stars, the binaries going around each other, what we observe, what we measure, and to produce all those is the contrast of the fringes. So we measure the light band to the dark band. And that tells you something about the actual size of the object you're measuring. And if you do that a lot of different ways at a lot of different resolutions, you can produce an image. Your eye is doing this every time you look through a telescope kind of automatically. A normal telescope has basically infinite number of apertures that it's within that lens or mirror. And for us, we're just sampling a couple of them. And it's a kind of an abstract thing, but in the end, let me see, I've got an image of fringes. We all get relatively obsessed with basically squiggly lines. And as you learn the science, it gets great. It's a little weird at first, but let me show you this. So this is, a star here. And this is for the VLTI, another interferometer. The light can be thought of propagating as a wave. So it's got just this wave front. It hits one telescope, and then it hits the second telescope. The light's directed to this delay line so that this light is slowed down by giving it more path to travel. And then at the detector, these are the fringes. So this is be a very high contrast, high visibility fringe. It's got very light, bright, and very dark, dark. And if it was a resolved or partially resolved surface, the contrast here would be less. It would be kind of bright gray and dark gray instead of white and black. So it seems kind of like a stretch that we can produce images out of this, but it's a very mature science, and it goes back to fundamental physics. I think I have another image somewhere. Yeah. So when we say fringes, here's an example here. This would be a very high visibility and a very low visibility. So this is a tiny star, meaning it's under resolved. So it means visibility here we would say is 1. This is a big star. Visibility here would be like 0.1. So by comparing the contrast of these, say if I had a fringe that was halfway between these, I would be able to tell you that the star must be smaller than this one and bigger than this one. But this squiggly line is what we call a fringe.
Yeah.
And so how do you go from those wonderful fringes to an image and to usable data that we might see in a paper?
Yeah. A whole lot of math. It goes into what's called Fourier analysis, a Fourier transform. And this is the same kind of math that is used in signal processing all the time for like audio or for stuff like if you ever use Photoshop or do image processing, the blur filter, like what's going on, my background here is blurred. It's a Fourier transform, and then that transforms spatial resolution into frequency. And so if you want to blur something, you get rid of all the high frequency information. Or if you want to make an MP3, you throw away all the frequencies that we can't hear, and that means your file size gets smaller. So this is all kind of the basis of a lot of different parts of STEM is this mathematical process. And you can do the same thing with an image, and that's what we do with reduction code. But we always are second guessing it. We have ways to calibrate it. We have checks. We have every couple years, we have an interferometry beauty contest where you try and produce the best image possible they give you some data and then say everyone tries to produce the best image, and then it's compared to the known truth image and see, and this is a way for us to competitively test our different codes to see that they're making sense. You simulate data, you test against the simulated, and then you know that it's working like it should. And then when you have something that's not a simulation, you can produce an image and trust it because, well, it works in every way you can possibly test it. Science is always about making your best effort and then second guessing it and having other people check it and then other people check them.
That's right. That's right. Yes. And so going back just a bit to Fourier transforms, we got a question from Brian, and Brian asked, what kind of math do you use the most? Calculus, linear algebra, differential equations, or something else?
I think pretty much all of it's been used at some point. Depends on what you're doing. If I'm doing alignment of the telescope or designing a first pass of designing an instrument, I may use geometric optics, so just geometry.
Yeah, a lot of trigonometry for me.
Yeah, a lot of trig at first. But then if you're doing data reduction, you're doing Fourier transforms, a lot of linear algebra, the wavefront sensors and the deformable mirrors, the adaptive optics. That's all a lot of linear algebra because it's a big matrix equation. So yes, we use all of it. Different specialties for different purposes.
And so for data analysis, I don't know how many students in our group here are in programming classes or are considering doing something in that field. What kind of training do you provide to support scientists who are using CHARA and doing their data analysis?
Oh, Cyprian, I'll let you take that one. That's your role.
Um, so basically we have so when we have the data, we need to reduce them. And I'm happy to show astronomers how to reduce their own data and use the tools that you have, because each instrument will have its own reduction pipeline with some specificities. So yeah, you're happy to teach them how to use it and what are the parameters that you need to tweak to make sure that what you get is correct or not, like checking for if the calibrators are indeed single or if there is signal of binaries in them, making sure that when it's crashing, why is it crashing? Is there something missing? Yeah, sorry for that. And yeah, there is that. And once the data are reduced, depending on what you want to do for science. So if it's a binary, if it's a diameter, if it's an image, it will be a different set of tools that you want to use to analyze them. So for the binaries, there is multiple software that back in the time, like 20 years ago, everyone would build its own. And so now there is a few that are used regularly. And so yeah, just pointing them to which tool may be more appropriate for what they want to do. Because for a single binary that you are just having your two star and you want the position, we have what we call Candid, which is a software to do that. But if you start to have to resolve one of the star and it has a disk or something, you want to add something, then we will use another tool that allow to do that, which is PemoRed. And so things like that. For imaging, there is a lot of different softwares.
Yeah.
And usually for a paper, you will use two or three of them to see if they give approximately the same features and the same answer. And that would validate your image in the end, things like that. So yeah, it's really depending on the science. And with that, you can pick and choose which one are more appropriate for what you want to do.
And I'll add, like, generally, like, what you want to do is in STEM in general is the simplest tool that will get you what you need. Start with that one, and then you add complexity only as you need to, right? If I'm just trying to get a binary or a diameter of a star, I don't need to use the imaging code. The imaging code is way overkill, and there's a lot of parameter space, and there's a chance I'll do something wrong. So start with the simple thing, and then you add on to it.
I love hearing those best practices. Perfect, perfect. And thank you, Cyprian. So of course, you have lots of data that you help scientists to get, and of course, for a certain amount of time, it's embargoed. After that embargo period, does that data go to an archive that's publicly accessible that the students may be able to explore and possibly use and doing some of their own research?
Yeah.
Yes. GSU, so Georgia State University, has a database in Atlanta. So we are transferring the raw data to Atlanta. And then from there, so for, as you said, a period of time, it is proprietary to the PI of the science program. So for us, it's 18 months, so a year and a half. Unless it is a student or a long program, then there is exceptions because the student may need more time to analyze their data and stuff like that. And for long program, if you need to observe for 3 years, you cannot publish the data before you're finishing observing. So you need to wait. But so typically it's 18 months. And after that, it is publicly available. It is also always good practice to try to see who it was, who owns it at the beginning, to ask them if they want to help you or participate in the project that you want to do with those public data, because usually it's very poorly seen if you take data without saying anything and publish a paper and stuff like that. And the owner of the data sees that,
Yeah.
and like all the community will be like, that person is not, maybe don't work with them. So always be a polite, ask the permission, see if they want to participate as well. And so to actually yeah, access those data, you can go on the CHARA website, and there is a whole description on how you can ask the access to the remote machine, because it's a remote machine that you can access the data on. And so you will need an account so that we know which data you have access to or not, and stuff like that. And so it is described on the CHARA website, and everyone can ask. And Jeremy, which is our data scientist that is actually based in Atlanta, will create an account for you and give you access to the data that you want to access and stuff like that. So everyone can ask to access the data. And of course, if it's public data, you can access them. Just, yeah, try to be nice and ask. Even if it's public, try to ask the people that took the data to see if they want to do something with it.
Thank you so much for making sure that we are using proper etiquette when accessing archived data. And yes, I've put a link to the CHARA database here in the chat. And just as Cyprian mentioned, it says that you should contact the CHARA data scientist, Jeremy Jones, to set up an account for the remote data reduction machine to access that archive of raw data. And the email for Jeremy is there at that link. So let me just pause and check in the chat, make sure I'm not missing any questions.
While you're doing that, I just want to say, like, if you're considering grad school in STEM, one of the things I recommend is see what type of stuff you want to study, see who is doing that work, and email that professor and see like what try talking directly. Or same thing with papers that are behind a paywall. So you really want to read this paper, email the author. You can get the paper for free typically by just asking the author, and they'll give you a copy of it. But finding out what type of work you want to do and then aligning yourself toward that tends to be a pretty good way to go about it.
Yep.
Okay, I don't have any more questions at the moment in the chat. So I have a question for both of you. What got you interested in astronomy in general? Can you tell us a little bit about your journey, Nick?
Sure. I think as a little kid, I went to Meteor Crater, and seeing Meteor Crater as a kid had a big impact of, no pun intended, of just I something from space could do this, got me really curious about space, and then I kind of put it in the back of my mind. I started as a photography major and film, and was interested in art and cameras. And the nerdier I got about cameras, the more I got a little curious about light and got curious about physics. I ended up a physics major. And then if you want to build cameras and not build weapons, astronomy is a good way to go. So I decided to put physics toward doing astrophysics instead. And I heard about a lab instructor I had for my intro astronomy course, saw a talk by Hal McAllister, who helped build the array in the first place, and said, "Yeah, you like building hardware? You should check out this Chara place. They've got a lot of hardware." And so I looked up GSU and applied to come here.
Wonderful. Thank you, Nick. And Cyprian?
For me, it was actually beautiful pictures of galaxies and stuff like that. Yeah, so my parents got me a subscription to a magazine which was about astronomy. And so, yeah, seeing the beautiful pictures, reading about the science just got me directly when I was like, I think I was 12, and I decided I want to be an astrophysicist. So, yeah, that's how I started. And at the beginning, I wanted to do dark matter, high energy cosmology, but then I got quantum mechanics classes. And even though I love hearing professors talking about it, I hate the mathematical aspect of the quantum mechanic. And so at that time, I had a lab, an optical lab class, and I just realized that I was really good and I loved playing with the lenses and stuff like that. And so I was like, oh, actually, maybe just instrumentation might be good. And with a couple of professors that I had during my master degree, just directed me to where I should go, trying to fulfill this field for instrumentation, but as well astrophysics. And so uh, managed to get my PhD doing astrophysics and instrumentation at the same time. And so now I'm at CHARA, where it's actually I'm using both of them pretty extensively. So yeah.
Thank you, Nick. Thank you, Cyprian. And so, as we are in our last about 14 minutes here, I would just like to kind of take a broader look at astronomy in general and look at the place that CHARA has in major facilities. For example, we have the Vera Rubin Observatory, which is now online. So exciting. And you've mentioned Gemini before as well too. Gemini will be doing, of course, its own work, but also doing follow-up observations in support of Rubin observations. Does CHARA play a role like that, have a function when it works with other facilities and doing follow-up and confirmations of targets?
Yeah, like Capital Worlds Observatory, we have a program for there's a PI that's put in to do follow up for it and candidate selection. Because again, we can get really precise measurements. The limitation we have is again the sensitivity. Um, so the place where we're at as far as like a national facility or anything like that is that it's a place where if there is future investment in astronomy, I think it's a obvious place to put it. I'm biased, of course, but an obvious place to put it is in interferometry because it's a proven technology. It's got a very healthy community that is always growing and more people using interferometric data in other papers. And it could be applicable. And like one of the things that Cimaril, that Cyprian's working on for higher sensitivity, is we can actually measure the diameters of active galactic nuclei. So not just stars, but the supermassive black holes that are actively feeding at the cores of other galaxies, we can measure the size of those directly. And so the motivation behind Cimaril sensitivity is to be able to observe more of those. And it's one of those things of we also are a teaching facility, and that there's no other facility like this in the world where you can bring a student can come and an astronomer can walk through and learn how to do interferometry from interferometrists. Um, we also are welcome people coming into the consortium, bringing new technologies or new things to try. One of those combiners in the lab is called Chariot. It's a CHARA integrated optic test bed. And the whole basis of it was contacted from groups of optical engineers that were not astronomers, not observationalists, but testing new techniques of integrated optics. So photonics, the analog to what electronics is for light is photonics. So inscribing with a laser in a chip pathways for light to go through and having optical circuits. And so we've built this instrument for them to be able to test these on sky. We have collaborations with like Brookhaven National Lab doing quantum teleportation experiments. So how do we get the next generation of transporting light between telescopes? Can we teleport light between the telescopes directly instead of having these physical connections or vacuum tubes? We're working on fiber optics between telescopes. So we have experiments there to extend the baselines. There's ideas of developing adaptive optics so that we could do open air propagation of light and use the adaptive optics to correct any turbulence from the ground. So there's a whole lot of different layers of things going on at Chara that really were just like many places funding limited. We could have a next generation facility building off of what we've already done here, and it's really unique facility.
Yeah.
Wow.
And yeah, talking about so follow up and things that we do with other facilities. The optical instrument speaker that we have has been made to be able to follow up, test, and plateau stars to characterize them. So their diameters with a very high precision, their limb darkening, because when you look at uh, the edge of the star, you're starting to have it's become more dark, less light, and so we need to characterize that so that we can then characterize properly the exoplanets that pass in front of them that are seen by Plato and TESS. So we do that. We are also complementary with what we call the VLTI, so Very Large Telescope Interferometer, which is on the southern hemisphere, but we can see some of the same system. So, for instance, for Betelgeuse, as Nick was saying, we are over-resolving it. So we were using CHARA for the very fine details, VLTI, which is so also doing interferometry, but with less long baseline, so had less finer detail, but more the big detail, and the LBTI, so which was it, long binocular?
Large binocular.
Yeah, And so with this one, which is just like a couple of meter, I think.
12 meter, I think.
Yeah, so a few meters away, we just have the big pictures, and so we get all of that together to actually have the imaging of Betelgeuse, for instance. And yeah, we complement spectral velocity, so you can detect very close companion with the spectrum of a system. So we have the spectral line that moves back and forth with the movement of the stars, but it have some information missing, and so with interferometry we can actually get this extra information that I need to actually completely resolve the orbit of a system and stuff like that. So yeah, we are complementary with a lot of things actually.
Astronomy, it's very much like a big puzzle, right? You know, biologists that can grow their thing they're studying in a petri dish and look around it. Astronomy, we have a lot of missing angles, right? We can only see something a certain way. And people are often confused of like, why are there so many telescopes? Why are you traveling to different places? Each one, each camera, each instrument, and each telescope has a different specialty, and they all do different, add different pieces to the puzzle. And so you first think of like, well, what's the question you're trying to solve? And then what data do I need to solve this question? And then that directs, well, I need data from this telescope and this telescope and this interferometer, and then I can answer my question.
So Brian has a question about AI and how it's currently being used in your work. Uh,
Sure.
do you see it becoming more central to astronomy research in the future?
Large language models have been used in astronomy for quite a while. Large language models are fine. They're a constrained problem where you train it on a very particular thing. They're used in theory a lot. What we call generalized AI or the public conception of AI, however, like ChatGPT and all that, um, there's still the problem of hallucinations and inaccuracy. So there are people that use it for since we're multilingual and a lot of people use it for translation. Works pretty good for that. Some people use it to clean up their code. It's okay for that. But for the actual science or anything that's really critical, we still steer away from AI in the places that are mission critical because if it's 80% right and 20% wrong, it's 100% not trustworthy. And it cannot AI ask general AI something you actually know, and you realize, oh, if you ask it something you don't know, it sounds really good. If you ask it something you're an expert in, you'll start to see, oh, it's not as good at this as I thought. Um, the places where we will use it are things like we have algorithms for aligning beams, we have many mirrors that control it once. There's again, that's a very constrained problem where we could train it carefully and it do exactly what we want. But in general, with science, like, you know, it's not going to cause breakthrough. It's not going to do anything innovative and creative the way that humans do science. It's not actually thinking. It's a useful tool, and in some places it lessens workload, in some places it increases workload. So picking where and when to use it is definitely an important part and a ongoing debate among scientists.
Yeah, and when you use it, make sure to check what it gives you. Would it be for an answer for a question that you had, or just writing a code that you want to do something? If it's a code, test the code, make sure that it does what you want, because it will sometimes not do it at all. And if you don't check, you can make the whole chains of things being wrong after that. So.
And a critical part of science is being able to reproduce what you do and explain every step you do. And a problem with AI is it is a black box and it cannot often reproduce what it does, right? It has no long-term memory. So if you can't explain what it did and you publish this, that may be an ethics violation. Like you need to be able to justify every single step in science. And you can't publish a paper and then say, well, I asked the AI and it told me this, and that published that. That's a good way to lose your reputation and get your paper ripped to shreds. We have to know what we're doing at every point.
Yeah.
So I was going to ask if you had any advice for these students as they continue in their studies, but you've already given so much right now, just in relation to AI, which outside of the large language models, using, what is it, Gemini and ChatGPT and other things as a tool for basic things is totally okay, and I think we've become comfortable using it. But I'm very happy that you gave that caution to all of us, but especially to these students as they go forward. It is so important that you have the knowledge to do what you are attempting to do, and that we use these AI resources as the tools that they are meant for, and not as a replacement for us thinking and doing the complex analysis for us, because then we certainly lose out, as you made very clear.
You lose the skills, and also AI will lie to you. You know, if you ask it to give a citation, it's so many famous examples of it just making up citations. At least Wikipedia, you can check those citations.
Right, that's a great point. Absolutely, absolutely. So let's see, we have about 3 minutes left. I'd like to invite the STEM coordinator. This is Crystal Ing. Crystal, would you like to join us and speak to the students as we wrap up? I'm looking for you, Crystal. Let's see. Oh, there. Crystal.
Saw her there a minute ago.
Yes, I did see her a minute ago, but I don't see her now. And that's okay. But she did say thank you all so much for being here, and directly to Nick and Cyprian. This has been a highlight of their STEM week, and they're very much looking forward to connecting with both of you again, and with Chara.
Oh, great.
Now, I do think that you have, well, students, anyone can come up to Mount Wilson. When is Chara open to students who may want to kind of see you in action and ask questions?
We have an exhibit hall that's open same time Mount Wilson is open. So there's the Mount Wilson Observatory has its own museum. You can walk up to a viewing gallery of the 100-inch and look in at the telescope there. You can walk around and see all the different telescopes up here, and we have an exhibit hall and interferometry. If you're a student and you'd send me an email and arrange a time that I'm up here, I'm happy to show people around in person.
Wow, that is fantastic. I definitely recommend each of you doing that if possible. You will not regret the experience. It's incredibly informative and exciting and fun, let me tell you. I'm definitely looking forward to coming back myself when I get the opportunity.
Please, anytime.
Thank you so much. Nick Scott, Cyprian Latherman, you have been absolutely incredible. Thank you so much for hosting this session for the students at the Los Angeles Pierce College.